Well, this is lecture 29 of Basic Calculus 1. In the last 1 or 2 lectures, we had covered the fundamental theorem of integral calculus, or we just say fundamental theorem of calculus, and then some of its application to problems. So, today we will be discussing rule of substitution, which greatly simplifies our work while doing integration of some functions. We will see how does it go. So, first thing is rule of substitution does not come out of the blue, it comes from the chain rule for derivatives. So, recall that the chain rule says if you have a composite function like g of f of x, then suppose I write that as g for simplification. So, dg over dx will be equal to dg over df times df over dx when you take the derivatives. That is what the chain rule for derivative says. Now, if you write in the prime notation, it will be g prime of f of x into f prime x equal to the composite function g of prime. Okay. So, now we translate that into integrals. You will look at the integral, suppose it is in the form the integrand, the function to be integrated is called integrand sometimes. So, in this integral, for example, you have integral a to b g of f x f prime x dx. So, integral a to b and dx, this is our notation for integral. The integrand is the other one, that is g of f of x into f prime x. So, that is our function now to be integrated. Now, when you write g of f of x into f prime x, so it looks like the earlier chain rule. We want to see how the chain rule is applied. So, it will be something like your, if you go to dg by dx equal to dg by df into df by dx. So, that should be equal to g of u prime, right. That is how it would look. So, it would translate to if u equal to f x, these are all necessary condition we need to put this composition work. Let u equal to f of x be continuously differentiable on the closed interval a b. So, its range automatically is a closed interval, right. It is a continuously differentiable function. So, once it is continuous, its range will also become a closed bounded interval. So, call that range as the interval I. Now, suppose g is also continuous on I. So, that means you have f that takes a b to I and then I is taken to r by g. So, your composite function g of f is defined from a b to r. Now, it says what happens to a b integral in terms of g of u, fine. So, that we can just write g of u instead of u, you can think of let us look at the second one, that will be easier to see. Indefinite integral g of f of x is the composite function times f prime x dx. So, that is same thing as g of u du, where this u is really an abbreviation for f of x. Okay. So, that means we are concerned about the function g, integrate g of u, it is same thing as telling write g of f of x and f prime x dx. Now, in terms of the definite integral, when you have the limits, in the first left side you have the limits for x as a to b, on the right side you have limits for u which is f of x, which are f of a to f of b. That is how they are related to the chain rule. We will see throughout the proof how it goes, why chain rule is used there, it will be obvious from the proof. Okay. So, let us try to prove this. We have g of u. So, remember g is from I to r, we are writing g of u, u belongs to I, and we have f from a b to I, that is how it is. So, now g of u is also continuous. So, let us write g prime u equal to g of u, it can be integrated. right? It is continuous on a closed boundary interval. So, we can write that as g prime of u. It is a primitive or it is called the antiderivative of g. Its antiderivative exists, so call it capital G. So, that means g capital G prime of u equal to small g of u. Okay. So, once you apply the chain rule, it gives capital dg by d of x equal to dg by du into du by dx, and dg by du, which is g prime u, that is equal to g of u, and then du by dx, because u equal to f of x. So, that is f prime x. So, that is how we obtain g of f of x into f prime x, which is equal to dg by dx. Fine. So, then you use fundamental theorem of calculus, because integral of dg dx, that is what is here, integral of dg dx will be equal to integral of g of f x into f prime x. Now, dg by dx we can write dg of f of x by dx, which is same thing as g of f x evaluated at a and b, right, because it is derivative, its integral of the derivative equal to that function. So, you get g of f x evaluated at a and b, and that we can again write g of f of b minus g of f of a. So, which also we could have written g of u, where u is from f a to u is from f of b, and we can again rewrite that integral f a to f b dg by du, again it is dg by du, which is equal to g of u. So, we write f of a to f of b g of u du. It is really variable of integration is u. So, it means f of a means u equal to f of a to u equal to f of b. So, that is what our first thing to be proved, integral a to b g of f of x f prime x dx equal to integral f a to f b g of u du. Okay. This is in terms of definite integrals. Now, similarly in the indefinite integral also it will happen, but now let us see u is equal to f of x. So, we can see that how the limits are coming in an alternative way, u equal to f of x. So, when x equal to a, u will be equal to f of a, and when x equal to b, u equal to f of b. So, directly you can see that by taking the indefinite integral, we get integral g of f x f prime x equal to integral of g u du. But again this one we can really take it as a rule and make a simplification instead of going through this composition and all the others. So, we now look at that in a different way, the same thing, but considering the differential. So, suppose u equal to f of x, that is what we have taken there. Now, its differential is du equal to f prime x dx. Then in the indefinite integral g of u du, you think of g of u, which is g of f of x, and then what about du? Du is f prime x dx. So, you just substitute that here. So, it looks, because of this dx in our notation, this is really going through very well. See, this looks trivial, why we are so concerned about it, but you think of this dx as if something like it is integral in say phi of x dx, that is our notation, but it means integrate phi over x or phi of x with respect to x. So, instead of dx, suppose we had with respect to x, we would have given this notation in the beginning. Then this does not seem to be very obvious, it requires a proof. But after proving it, we find that if you consider the differential, this f prime x is nothing but f prime x. So, it looks something like in the new one, f prime x with respect to x will be equal to with respect to u. So, instead of writing this with respect to integral and so on, we would say that this is really the differential. If we take this to be differential, this is also differential of u, as our rule says. That is why we can really substitute. We just find out, say u equal to f of x, we substitute, then you get f prime x dx, the differential, as du. So, that is g of f of x becomes g of u prime dx, and which is the correct one? That gives now g u prime dx as a differential u prime dx is du. So, you get directly whatever we have proved in the theorem. So, see that our notation, instead of writing with respect to x, since we have written dx, that notation is really helping us now, and this notation is consistent with the chain rule or the rule of substitution. That is why this is called rule of substitution, which is in disguise the chain rule for differentiation. So, see that this notation really helps, and we can treat that dx in the integral as the correct or as the actual differential. Okay. So, since we are able to consider that as the differential, now g u du, if you substitute u equal to f of x, that gives rise to the left hand side, because the differential du becomes f prime x dx. That is why of course, this notation was given, and because these things are consistently going through the differentials, we make it a rule, it is a mnemonic. Instead of using the theorem in that form always, this will be a convenient form, which we call as rule of substitution. Okay. So, what we have to do really, if we find somehow that some functions in the integrand will be simplified, if I substitute u equal to f of x, then we substitute and see that when x equal to a, for the limit of integration, u becomes f of a, when x equal to b, u equal to f of b, and in that case du is also equal to f prime x dx. So, in the integral a to b g of f x f prime x, if we go on substituting whatever we have seen, we directly get our result. Fine. So, this is just a magic of the notation, so to say, but we can use this as a mnemonic and continue with our integration. Let us see an example how it is applied, rule of substitution. So, you see here we have to evaluate minus 1 to 1 3x square root of 1 plus x cube dx. Now, it looks difficult to do, because we know only polynomials are x to the power something and so on, nothing more. But here what happens, 3x square dx is really derivative of x cube or the differential of x cube equal to 3x square dx, right, dx cubed by dx equal to 3x square. So, now the differential is like this. Also it is square root of 1 plus x square, 1 plus x cubed. So, derivative of 1 is also 0. So, instead of x cubed, we could have considered d of 1 plus x cubed, fine. So, 3x square dx can be thought of as d of 1 plus x cubed. So, it looks, if we substitute u equal to 1 plus x cubed and apply the rule of substitution, that would help us to integrate. Okay. So, let us try that. Substitute u equal to 1 plus x cubed. With that substitution, the differential du becomes 3x square dx, and we have to be concerned about the limits. When x equal to minus 1, substitute in u. So, u becomes 1 minus 1, which is 0, and when x equal to 1, substitute here, it is 1 plus 1 equal to 2. So, the integral minus 1 to 1 3x square, this can be written as, now integral in u, which is square root of u, and the other one is du 3x square dx, that is du, and the limits now become in u, they are 0 and 2. So, it is 0 to 2 square root of u du. Now, this will be easy to integrate. We know exactly its integration, it will be u to the power half plus 1 divided by half plus 1, or that is 2 by 3 into u to the power 3 by 2, evaluated at 0 and 2. So, that simplifies to 4 times root 2 divided by 3. This is how the rule of substitution is used. So, sometimes when you get experienced, we will simply start like this, it will be equal to integral. Now, 3x square dx is really d of x cubed or d of 1 plus x cubed. So, you write 1 plus x cubed and d of square not square root 1 plus x cubed. Then integral will be minus 1 to 1, or if you go through the indefinite integral, it will go through, that will give you really 2 by 3 it is as if it is u and then 1 plus x cubed to the power 3 by 2. This has to be evaluated. Now it is in x, we are not worried about u, it will be minus 1 to 1 and then that will simplify to 4 root 2 by 3. But do it after some time, not now. Substituting will be easier to see instead of going directly through that. Okay, let us go to next thing, which is the indefinite integral. So, now if you go for the indefinite integral, it will not have any limits here. It will be 3x square square root of 1 plus x cube dx, which is integral root u du and this plus c, because indefinite integrals will introduce a constant. So, that will be 2 by 3 into 1 plus x cube to the power 3 by 2 plus c, as we have seen, fine. But we have to remember that in the indefinite integral there can be an arbitrary constant. That is how the indefinite integral will look like. So, then if you know the indefinite integral from minus 1 to 1, when you integrate, you just come to here and then evaluate it at minus 1 to 1 for x, right, x equal to minus 1 to x equal to 1. So, this is after a bit of experience, immediately you can see, even you do not need to put that u equal to 1 plus x cubed, but directly do it. So, then as we know, it simplifies to 4 root 2 by 3. So, either way you can do it directly through that, when x equal to minus 1 equal to 0, changing the limits for u, or find the integral in terms of x and substitute. Okay. So, let us take another example. Evaluate derivative with respect to x of integral 1 to x to the power 4, not x, it is 1 to x to the power 4 sec t dt. So, sec t dt will be difficult to integrate, right. We do not have a formula. Had it been secant square, yes, we could have done it, it will be tan, but it is secant t dt. So, maybe we have to use fundamental theorem, but fundamental theorem says that derivative, that is d by dx of a to x, but it is x to the power 4. So, what we do? We can find out the chain rule, say express this as d of dx fourth and then convert it to d dx. That is what we do here. We substitute u equal to x to the power 4, because that is where the trouble is, and use the fundamental theorem. So, now d dx, d by dx of 1 to x fourth secant t equal to du, x fourth is, that is u now. So, derivative of that is derivative of this with respect to u into derivative of u with respect to x, fine. So, that is how it looks now. So, that is equal to derivative with respect to u of integral 1 to u secant t dt times derivative of u with respect to x. Now, here we can use fundamental theorem. So, that gives us secant of this variable, that is u, this a is gone, is 0 derivative. So, secant u, that gives secant u times du by dx, u equal to x to the power 4. So, that gives 4 into x cubed. So, substitute u back, you would get 4 x cubed into secant of x to the power 4. So, you see we did not have to worry about what will be this integral, but since it is differentiation of an integral, we could do it, but with rule of substitution. Okay. Let us go to next example. Here we have to evaluate phi divided by 4 to pi by 2 integral and cot theta cosec square theta d theta. So, it should strike something, we have cot theta, we have cosec square theta, but derivative of cot theta is minus cosec square theta. So, we can introduce a minus sign and substitute cot theta as something, so that the differential cosec square theta d theta will be minus d of u, if u equal to cot theta. Okay. So, let us try. Suppose we substitute u equal to cot theta, then you get the differential du as minus cosec square theta d theta. And look at the limits, when theta is pi by 4, our u becomes cot of pi by 4, which is 1, and when theta equal to pi by 2, our u equal to cot of pi by 2, which is 0, right. So, our limits will become from 1 to 0, that is the integral we can write as 1 to 0 cot theta, which is u, and differential is du equal to minus cosec square d theta. So, cosec square d theta is minus 1 into du. So, it is in the form u minus 1 into du, but it is 1 to 0 limit. So, we can change that with this negative sign, that will be 0 to 1 u du. Now, this we can integrate, it is u square by 2, and then you have limits as 0 to 1. So, at 0 it is 0, at 1 it is 1 by 2. So, it gives 1 by 2, that is the answer. So, see, this is how we will be using the rule of substitution. That will be more convenient than directly also doing, but sometimes if it is bigger expression, we can see directly and then substitute appropriately. Substitution will minimize mistakes instead of doing directly.